Okay, we're continuing with Chapter 4 in the chemistry textbook, which is on reactions in aqueous solutions. Previously, we've gone through the opening section, which is on general properties of aqueous solutions. And the purpose of this section, along with there was another video that was sort of an enhanced version of this section. The purpose was that this was sort of a primer for the remainder of the chapter. Because in this chapter, we're studying reactions in aqueous solutions. And so we needed to be clear on what exactly is an aqueous solution. What does it mean for a substance to dissolve in another substance? What does solubility mean? What about electrolytic properties of substances? What does it mean for a substance to be a non-electrolyte, a weak electrolyte, or a strong electrolyte? What's the difference and the relation between solubility, dissolving properties, and electrolytic properties? Okay, so now that we're clear on these concepts, we're going to get started with studying three of the primary types of reactions that occur in aqueous solutions, in nature, in biological processes, in industry, etc. These are precipitation reactions, acid-base reactions, and oxidation-reduction reactions. So in this video, we're going to talk about precipitation reactions. Okay, one common type of reaction that occurs in aqueous solution is the precipitation reaction, which results in the formation of an insoluble product or precipitate. A precipitate is an insoluble solid that separates from the solution. Okay, so with any reaction in aqueous solution that we're going to study in this chapter, but really any reaction in general, the idea is that the way we're going to conceptually visualize and interpret what's happening is that you start off with this, you can think about a beaker of pure water, okay? And then from there, you're going to add to that water two or more compounds that in general are going to be soluble in water. Or you could also look at it like you've got two or more beakers of water, two or more separate beakers of water that you add single compounds to those beakers. And so now you've got these different beakers with aqueous solutions of a single compound, and then you mix those beakers together to where the result is you've got this single beaker of water with two or more compounds that were initially separate now dissolved in the water. And so what happens is, because we understand what it means for something to dissolve in a solvent, like water, for example, the result is that you're going to have these particles floating around in the water. They're either going to be ions or they're going to be molecules, right? And so they're completely separated. They're floating around and they're mobile in the water. So everything gets to interact with everything. You have these separate compounds with these ions or molecules that even if you mixed those compounds together outside of water, the different components wouldn't be able to interact, at least in any way close to the degree that they can interact when dissolved in water. Why? Well, because there's two things that happen upon dissolving in water. First of all, the ionic compounds, for example, are completely broken up out of their lattice structure, right? The ions just separate, or even but if it's not an ion, like sugar molecules, the clusters of the sugar completely separate. But then furthermore, it's more than that. These particles are also completely mobile in water as well, right? So the result is that everything can interact with everything, to where before, when they were separated, that couldn't happen. And so the idea is a reaction potentially takes place because once you have these two or more compounds dissolved in water together, now these components that couldn't interact before can interact, and maybe these new interactions cause something different to happen. That's the idea of reactions in aqueous solution. Okay, now one potential outcome of doing this, of adding different compounds to the same water, and these compounds are in general going to be soluble, right? One potential outcome is that when new components interact, these new components, when they come together, they form a combination that isn't soluble in water. And so a solid comes out of the water or precipitates out. A precipitate forms. An insoluble solid separates from the solution. And these types of reactions are called precipitation reactions. Okay, precipitation reactions usually involve ionic compounds. Okay, so yeah, we're in this chapter, for any of the precipitation reactions we study, we're strictly going to be analyzing ionic compounds. So the solutes that are brought in and added to the water together are always going to be ionic compounds when we study precipitation reactions. But for other reactions, we could mix in ionic and molecular compounds. But it says usually. It's not like you can't potentially have a precipitation reaction that involves a molecular compound. For example, when an aqueous solution of lead-2 nitrate is added to an aqueous solution of potassium iodide, a yellow precipitate of lead-2 iodide is formed. And so here's the reaction. You've got this initial beaker, this one beaker of lead-2 nitrate, aqueous, and this other beaker of potassium iodide, aqueous. So remember, since the state is written aqueous, that means that these substances are dissolved. Aqueous, it's not just water environment. If you drop a rubber ball in water, the rubber ball's in a water environment, but you wouldn't put its state as aqueous. You would leave it as solid because it's not dissolved. So you've got these two compounds here, ionic compounds, are dissolved in water. You mix the two solutions together, so now you've got both of these compounds dissolved in the same beaker of water. As a result, but we know what aqueous means. In the context of ionic compounds as well, we know what aqueous means. In the water, you've got these lead-2 plus cations floating around everywhere. You've also got nitrate anions floating around everywhere, potassium cations and iodide anions floating around everywhere. So they all interact and they intermingle. These ions are completely separated and they're mobile. So now when the lead and the iodide, the lead cation and the iodide anion interact, the result is that, so if we happen to have in another project, if you were working with lead iodide, lead-2 iodide in another project, lead-2 iodide is not soluble. You put it in water, it doesn't dissolve, at least to any significant extent. So what happens is the lead and the iodide, the lead-2 plus and the iodide, they come together and form an ionic compound, and it precipitates out. So it's not dissolved anymore. This is written as solid. It's not aqueous. Okay, but now when the potassium and the nitrate interact, that resulting ionic compound is soluble, so this just remains dissolved. But it could have been the case, depending on the circumstance, where this combination also is insoluble, and you have two precipitates. Okay, so if we come to figure 4.3, we can get an illustration of this. Okay, so there the solutions are mixed, and there's the solid precipitating out, the lead-2 iodide. And so initially, you could think about like the instant that these two solutions are mixed, you just got these ions floating around, but they're mobile and they can interact. And so when the iodide interacts with the lead-2 plus, it precipitates out, but these two just stay dissolved. Nothing happens. They interact, but they realize, nope, we're insoluble, so they stay separated. Okay, the preceding reaction is an example of a metathesis reaction, also called a double displacement reaction, or a reaction that involves the exchange of parts between the two compounds. In this case, the cations in the two compounds exchange anions. So Pb2 plus ends up with I minus as Pbi2, and K plus ends up with NO3 minus as KNO3. Okay, so a metathesis reaction, double displacement. The general character of a double displacement reaction is you're starting with these two compounds, and usually it's ionic, but it doesn't have to be ionic. It's these two compounds, and after the reaction takes place, these two compounds have exchanged parts. A part that was something that was a part of one of the compounds and a part of the other compound now come together and there create a new compound. And perhaps the other parts also come together and create another compound as well. That's a metathesis or double displacement reaction. Okay, as we will see, the precipitation reactions discussed in this chapter are examples of metathesis reactions. So all of the precipitation reactions we're going to analyze, because we're just going to be dealing with ionic compounds, right? Okay, and what's going to happen is the one part of one ionic compound interacts with a part of the other ionic compound. The parts interact and they switch spots, right? That's the character of a metathesis or a double displacement reaction. Okay, solubility. So we can see that solubility properties of substances, of compounds, are a big part of a precipitation reaction, right? Because what dictates if a precipitation reaction is going to occur in aqueous solution, which means something needs to precipitate out, is going to be whether or not a resulting substance is soluble in water or not. That's what this is all about. Okay, but because the solubility properties of substances, are even inherently a part of everything we're studying here, right? Because to be an electrolyte, you have to be able to dissolve in water, right? But even more than that, to have any of these reactions take place, you need to be able to dissolve in water. The compounds that are coming together need to dissolve. So we've already talked about the meaning of solubility and just the meaning of dissolving properties. But this is where the textbook officially brings it up. So how can we predict whether a precipitate will form when a compound is added to a solution or when two solutions are mixed? It depends on the solubility of the solute, which is defined as the maximum amount of solute that will dissolve in a given quantity of solvent at a specific temperature. Right. So what we talked about was that if a substance is insoluble in water, then that means that it might dissolve to a small extent, but it's not appreciable at all. Like sand. Sand is said to be insoluble in water, but still a very small amount of sand still dissolves, but it's negligible. That's what's called insoluble. Okay, but if a substance is not insoluble, then what solubility is telling you about a substance is how much of that substance will or can dissolve in water before the solution gets saturated and no more can dissolve. And so really with these precipitation reactions, we're more focused on insoluble versus soluble and not so much about, the actual level of solubility, right? We're going to be asking, okay, is something soluble or insoluble? It doesn't matter the extent of if it is soluble, the extent of the solubility, right? And so if something is insoluble, then at a specific temperature, if you have a certain amount of solvent at a specific temperature, then a negligible amount of that substance is going to dissolve in the solvent, no matter how much you add. Okay, chemists refer to substances as soluble, slightly soluble, or insoluble in a qualitative sense. A substance is said to be soluble if a fair amount of it visibly dissolves when added to water. If not, the substance is described as slightly soluble or insoluble. Yeah, so there you go. It's like a qualitative. Insoluble is more of a qualitative description. It doesn't mean that if something is insoluble that there's just absolutely none of the substance dissolves whatsoever. No, it's more about if you add that substance to the solvent, and we're focusing on water, then do you pretty much see that nothing dissolves, that you can't really visibly see anything dissolving, even if you technically looked at it with a microscope and really analyze it to a fine extent, you would see that some did dissolve. In that case, it's still insoluble. Or maybe you can visibly see that some did dissolve, but it's not much, right? It's a little bit dissolves and then it just stops. But the majority of the substance remained undissolved. You might call that slightly soluble. But if in general you add a substance to water and it pretty much dissolves, like a decent amount of the substance or all of it dissolves, you call that soluble. Okay, now it says all ionic compounds are strong electrolytes, but they are not equally soluble. Yeah, exactly. This is why we wanted to make clear the difference between electrolytic and solubility or dissolving properties. All ionic compounds are strong electrolytes, meaning that if they are soluble to some extent, it doesn't matter how soluble any ionic compound is, it's going to have that full dissociation, non-reversible, into ions. But even for an ionic compound that's insoluble, so it would technically be a non-electrolyte, it might be soluble to a very tiny extent, right? If you zoomed in on it, even at that zoomed in level, it's going to have that strong electrolyte property. It's going to fully dissociate with no reversibility. So that's what they mean by, no matter what the context, all ionic compounds are strong electrolytes, even for like an insoluble ionic compound that's technically wouldn't conduct electricity. Okay, so with these precipitation reactions that we're going to be studying, we since we're only dealing with ionic compounds, we don't have to think about the potential variables that a weak electrolyte would bring to the table. We're either going to have insoluble ionic compounds or soluble ionic compounds, but all ionic compounds are strong electrolytes. There's no reversibility in dissolving taking place in these precipitation reactions we're studying. Okay, table 4.2 classifies a number of common ionic compounds as soluble or insoluble. Keep in mind, however, that even insoluble compounds dissolve to a certain extent. Yeah, similar with like a non-electrolyte. You might have a substance that, if it hypothetically was soluble, it would dissolve into ions, right? Like an ionic compound. But since it's insoluble, even if it dissolves to a small extent and it is producing a small amount of ions in the solution, it's too small amount of ions to conduct electricity, so it's a non-electrolyte. Okay, but now this table 4.2 lists different ionic compounds and the corresponding solubility in water at 25 degrees Celsius, room temperature. So we'll be able to reference this table to analyze precipitation reactions to see if precipitates are going to form, or maybe if the initial solute that's added to the water dissolves at all. We'll be able to come to this table and see if a certain substance is soluble or not. Okay, molecular equations, ionic equations, and net ionic equations. So we're going to learn the meaning of these terms in this section from the perspective of precipitation reactions. However, you're going to see that these equations can be applied to analyze any kind of reaction in aqueous solution. Really, any kind of reaction in any solution, but we're focusing on aqueous. So with acid-base reactions and oxidation-reduction reactions, we're going to be constructing the molecular ionic and net ionic equations. Okay, so it says the equation describing the precipitation of lead-2 iodide on the previous page, so this equation, is called a molecular equation because the formulas of the compounds are written as though all species existed as molecules or whole units. A molecular equation is useful because it identifies the reagents, that is lead-2 nitrate and potassium iodide. If we wanted to bring about the reaction in the laboratory, we would use the molecular equation. However, a molecular equation does not describe in detail what actually is happening in solution. So yeah, what they're saying is that, so we've got these ionic compounds in this chemical reaction, and some of them are aqueous. But we know that with an aqueous ionic compound, it's actually broken up into the individual ions. The individual ions are dissolved. But that's not indicated here. Anything that's dissolved that would break up into ions is written as aqueous, but it's left with its full chemical formula. That's the idea of a molecular equation. For a reaction in any solution, with a molecular equation, if there's certain compounds that have broken up into ions. So if you think about it in terms of dissolving, the only type of substance that when it dissolves is going to break up into separate particles is going to be an electrolyte, because a non-electrolyte that doesn't break up into ions is just going to, like sugar, it does the molecular formula of the substance stays the same, right? C12H22O11, it dissolves into individual particles, but it's still just hydrated aqueous C12H22O11. It's only electrolytes that actually break up, the molecular formula gets broken up. And so the idea is, again, with a molecular formula for any kind of reaction in solution, if you've got a substance that is an electrolyte, it could be an ionic compound, or we're only looking at ionic compounds for precipitation reactions here, but for any kind of reaction, if the substance breaks up into ions when it dissolves, and it is dissolved, in the case of water, it's aqueous, for the molecular equation, you don't write it as broken up. You still just leave it with its full chemical formula and just indicate its state as being dissolved. You do that for all of the reactants and all of the products. That's the idea of the molecular equation. And they're saying what's useful about the molecular equation is in particular in relation to the reactant side, because it tells you, it gives you a picture of how the initial reaction was created, what substances were used. Here you had a solution of lead-2 nitrate, a lead-2 nitrate powder, ionic compound, and a potassium iodide powder, ionic compound. Those two solutions were created, then mixed. Okay, so the first step for analyzing a reaction in aqueous solution is going to be to write out the molecular equation. You know how the reaction was created, all of the substances involved to start with. So again, with precipitation reactions, it's just going to be a bunch of ionic compounds, only ionic compounds, the ones we're studying. But in general, you just write out whatever was involved in the reactant. If it's dissolved in the water, you list it as aqueous. If it's not dissolved, you list it as solid or whatever. You just list out all the reactants. But again, with the molecular equation, it doesn't matter if something is dissociated in the solution. You leave its full chemical formula. And then based on your knowledge of the reaction, the type of reaction it is, you write out all the product substances. And if they're dissolved, you put aqueous. If they're not, you put the non-aqueous state. But again, it doesn't matter if they're dissociated. You leave all the full chemical formulas. And then you balance the equation. That's the next step. You see they have it balanced here. Okay, now from there, you're going to go to the ionic equation, which with the ionic equation, the general idea is what you're going to do is anything that's dissolved in the solution, if it's an electrolyte, which means it's going to break up into multiple components, ions, right? This wouldn't happen with a non-electrolyte. You're going to indicate that. Okay, so as pointed out earlier, when ionic compounds dissolve in water, they break apart into their component cations and anions. To be more realistic, the equations should show the dissociation of dissolved ionic compounds into ions. Therefore, returning to the reaction between potassium iodide and lead-2 nitrate, we would write, okay, so all they've done here is they've indicated, look, it's not PbNO3 units dissolved in the solution. It's Pb2 plus aqueous and NO3 minus aqueous and K plus aqueous, I minus aqueous, K plus aqueous, NO3 minus aqueous. But then this is not broken up, so they leave it solid. The ionic equation is just giving you a more realistic picture of what's happening in the solution, right? You have these individual hydrated Pb2 plus cations and these individual hydrated 2 minus anions initially floating around in the solution. Then they all interact, and you have the lead-2 iodide precipitates out, but the potassium ions stay in solution, and the nitrate ions stay in solution. This is a more realistic picture of what's happening, right? Now, but the disadvantage is, which you, in particular from the reactant side, is you can't see exactly how the initial reaction was created. What were the starting substances? You can't tell, right? It could be lead-2 iodide to start with. You don't know. All right. Now, something to note, though, that we're going to see in upcoming sections is that there is a little bit of a caveat in that. So you might be wondering, well, okay, so even if it's we have the criteria of, are we dealing with a weak or a strong electrolyte, right? In terms of breaking up into ions. Is it a weak or a strong electrolyte? Again, if it's a non-electrolyte from the sense that it's like something like sugar, this isn't, you're always going to have its full molecular formula anyway. Because even though it breaks up, it still doesn't, the chemical formula of the sugar doesn't break up. So there's no like, kind of ionic equation parallel for sugar where you're breaking it up into components. It's only with electrolytes. So with the ionic equation, when you're dealing with electrolytes in solution, the question is, well, what about weak versus strong electrolytes? So I guess we just break up weak electrolytes as well when we get to the ionic equation, and we're going to see the convention is that with the ionic equation, you only break up the strong electrolytes. If it's a weak electrolyte, but it's still soluble, then with the ionic equation, you're going to just leave it, non-broken up. But with precipitation reactions, since in this chapter where the precipitation reactions we're studying are only going to involve ionic compounds, that doesn't come into play because all ionic compounds are strong electrolytes. They're either insoluble or they're strong electrolytes. So everything with the precipitation reactions we're studying, everything that is aqueous is going to get broken up in the ionic equation. All right. Now, you can also notice here that you want to balance the equation, the molecular equation first, and then you're going to use those coefficients to, that's where, okay, so you have Pb2 plus with a coefficient of 1. Then you've got NO3 minus, but with a coefficient of 2. Now, you're going to have the K plus with a coefficient of 2 and the I with a coefficient of 2, I minus. You see, that's where the coefficients are coming from here. Okay, the preceding equation is an example of an ionic equation, which shows dissociated species as free ions. To see whether a precipitate might form from this solution, we first combine the cation and anion from different compounds, that is, PbI2 and KNO3. Referring to table 4.2, we see that PbI2 is an insoluble compound and KNO3 is soluble. Therefore, the dissolved KNO3 remains in solution as separate K plus and NO3 minus ions, which we call spectator ions, or ions that are not involved in the overall reaction. Okay, so what they're saying is, with the precipitation reaction, we started off by writing the molecular equation, which showed all of the ionic compounds involved in with their full chemical formula as the reactants, which in general for precipitation reactions, these are all going to be aqueous. They don't have to be, but for precipitation reactions in general, they're going to be aqueous ionic compounds. And then we just thought about, okay, you have all these ions in solutions, we can mix and match the different cations and anions and see if some are insoluble. If they are, you're going to write it as a solid compound, and then the other mixing and matching could be insoluble as well, and then you'll put that as solid or you'll leave it as aqueous. Okay, then you balance the equation, and now it's saying that the dissolved KNO3 remains in solution as separate K plus and NO3 minus ions, which are called spectator ions, or ions that are not involved in the overall reaction. So what are they talking about here with these spectator ions? What they're saying is that, we come back here, so here's the ionic equation. What they're saying is that if you look at the overall chemistry that took place outside of the dissolving process, because even dissolving is technically chemistry, but really with these reactions in aqueous solution, there's going to be the whole idea is there's going to be a chemical reaction that's going to take place in the solution outside of just like the dissolving process. There's going to be a chemical reaction that's going to take place. Well, if you notice here, the nitrate ions and the potassium ions were not involved in any chemical reaction here. All these ions, they got dissolved into the solution, and then they just stayed dissolved. They didn't do anything, right? Because if you come here, they're aqueous. They didn't make a precipitate. There was no chemical reaction. They started dissolved and they just stayed dissolved, and that's it. As opposed to the lead 2 plus cations and the iodide anions, they started off dissolved in the solution, but then a chemical reaction took place. Now it's PbI2. So these actually took place in the precipitation reaction that we're studying here. And so that's why they're calling these ions spectator ions. They're the same on the reactant side, on the product side, so you can cancel them. And when you do that, what you're left with is what's called the net ionic equation. So the net ionic equation, which shows only the species that actually took part in the reaction. Pb2 plus aqueous plus 2I minus aqueous gives PbI2 solid. So this is showing you the chemistry that took place, or more specifically the chemical reaction, the actual chemical reaction that took place in this aqueous solution. Really, all that happened from a chemical reaction standpoint, all that happened was that you started off with these lead 2 plus ions floating around the solution and these I minus anions floating around the solution. These ions interacted and formed a precipitate. That's what happened. That is precisely what happened. Okay, So you can see the difference between the ionic and the net ionic equation. It's not that the ionic equation isn't valuable, because it's giving you the full picture, right? It's giving you the full environment. It's giving you all the actual substances that were involved. But the net ionic equation is also valuable because it's just showing you strictly the chemistry that took the chemical reaction that took place. Okay. Looking at another example, we find that when an aqueous solution of barium chloride is added to an aqueous solution of sodium sulfate, a white precipitate is formed. There you go. It's a white precipitate. Treating this as a metathesis reaction, the products are barium sulfate and sodium chloride. Yeah, so what they're saying is you're mixing a metathesis reaction, you're mixing and matching the different components. Barium chloride they're both aqueous, it's telling us. So when you combine the solutions, you're gonna treat it as a metathesis reaction. You're gonna say, okay, what happens when the barium 2+ interacts with the SO4 2-, and what happens when the Cl- interacts with the Na+? And when you go to, if we look at the solubility table, you've got, so sulfates are all soluble with the exception of a barium. So barium sulfate is insoluble. What about sodium chloride? So, well, all compounds containing sodium are soluble, so not sodium chloride. So what do? All you do is you start off by writing the reactants, the reactant compounds with their full chemical formulas, but you indicate that they're aqueous. Okay, then for these precipitation reactions, we're going to mix and match the different cations and anions. They're all going to be interacting, and we see if any of the resulting interactions result in something soluble or insoluble. If it does, then that's going to precipitate out, and we're going to indicate that with the full chemical formula, but showing solid or whatever the state is. It could be gas, liquid, just it comes out of the dissolved state. Okay, and then all of the other cations and anions that interact, if those are still aqueous, we just write the full chemical formulas as aqueous. And then we balance this equation. Then we come to the net ionic or the ionic equation. And so with precipitation reactions, these are all going to be ionic compounds, so strong electrolytes. So anything that's aqueous, we're just going to break it up into the component ions and then put the correct coefficients. Do this on both sides of the reaction. Anything that's aqueous to get the ionic equation. Then the net ionic equation, we just cancel the spectator ions. Here, Na+ is spectator and Cl- is spectator. And you're left with the net ionic equation. Okay, so the following 4 steps summarize the procedure for writing ionic and net ionic equations, which right now we've only really looked at precipitation reactions, but we're going to see it's a similar process with any kind of reaction in aqueous solution, except that if you're dealing with a weak electrolyte, which you're never dealing with the equations we're studying with precipitation, you don't break it up into ions. You just leave it as aqueous even in the ionic and net ionic equations. The general idea is for any kind of reaction in aqueous solution, you're going to write a balanced molecular equation for the reaction using the correct formulas for the reactant and product ionic compounds. So they're just focusing on ionic compounds here, but you're really going to write out for any general reaction in aqueous solution, it could be ionic compounds, whatever, you're going to write out their full chemical formulas regardless of if they break up into ions or not. Or maybe they're not going to be aqueous, you just leave them as like solid metals or whatnot. Then you're going, for the product side, what you write on the product side is going to depend on if any substance comes out of the solution, becomes undissolved. And you're going to indicate that on the product side. And then anything else that just stays dissolved, you're going to indicate that as well on the product side as aqueous. But still, you're going to leave everything in its full chemical formula form. Then you're going to balance that equation. Then you're going to write the ionic equation where you're going to break up strong electrolytes into ions, and weak electrolytes you're going to leave with their full chemical formula on both sides, the reactant and product side. Then the net ionic equation, you're just going to cancel the spectator ions. And then it says check the charges and number of atoms. Yeah, if you balance the molecular equation appropriately and you transferred all those coefficients and subscripts to the the ions correctly, then everything's going to balance, the charges and the atoms.